Okay, our next speaker is Xander Hall from Carnegie Mellon, who is going to be telling us about using DESI as a transient discovery machine. Take it away.
Hi, yeah, so I'm Xander Hall. I'm a second-year grad student at Carnegie Mellon, and I'm going to be talking about using DESI in a somewhat unorthodox way. So, okay. So, for those of you who don't know, DESI is the stage 4 cosmology instrument that's on Kidd's Peak, and basically it's doing this sky survey where it's trying to get the redshift of 40 million galaxies. And it's actually ahead of schedule, and is now on track to sort of observe 60 million galaxies. It does this through this sort of a giant instrument where there's these 5,000 of these robotic fibers, which sort of patrol a certain area in the sky of about a few arc minutes in diameter. And basically 5,000 of these, and you can cover a 9 square degree area, and you tile basically across the sky with a fiber optic cable getting redshifts of all 5,000 galaxies at once. There's also sort of 3 channels here. So we basically get all the way from the UV to the near infrared basically in one go. And it's also a very decently high resolution spectrograph. So it's 2,000 sort of in the blue arm, up to 5,000 in the red arm. And also the throughput is extremely good. So you're getting like 70% efficiencies. And so that lets us go very, very deep. So we sort of have this problem with LSST and eventually with Roman, where we won't be able to observe spectroscopically every single thing that happens in the night sky. And basically, we're trying to augment that with DESI and this thing we're calling the spare fiber program. So as DESI sort of is going across the sky, you have all these fibers, which are going basically all the way across the sky. And then this yellow dot here, you can see there's going to be a supernova. And basically, we take one of the spare fibers from that would go on a galaxy here that there's no target perhaps in this region of sky, and we put a fiber on the galaxy, and then we can observe the supernova and get a really nice spectra, in decently high resolution as well. And basically, we're doing this by just scraping everything from TNS, scraping everything from GTF alerts, and then we also have our own DECAM project that we're getting deeper and deeper alerts for. And I think the very interesting thing is that we're actually able to get most of the targets that we do observe pretty rapidly. We get about 20% within 2 days of actually being observed, which, as Neil pointed out, like one day, it's not 6 minutes, you can get with SCDM, but 1 to 2 days, you can still sort of see these very narrow features. And since you have an R2000 to 5000 spectrograph, you can actually better resolve these narrow features. So I have here a sample sort of a lot of 1A supernova and then a lot of type 2 supernova. A nice thing about the high resolution is that you can get a lot of galaxy lines, so you can get very precise redshifts as well from these transients. You don't have to rely on sort of template fitting to be able to narrow down their redshifts. We talked a bit about IXF. So one of the things DESI did sort of in its commissioning phase was we did these giant spectroscopic catalog of IXF, and you can actually see various narrow features sort of appear and then disappear, and then you can see the p-signaling hydrogen eventually come out sort of later in the spectra. And it's like I said, this is a R5000 spectrograph, so you can really see all sort of the narrow features and how they evolve. And it's just a really, really great spectra that we can get out of this machine. Another interesting aspect of it is that DESI is just observing the nucleus of basically every galaxy out there. And as you do that, you're eventually going to pick up various nuclear transients. And so here, example, is 2 TDEs that I found that were previously unclassified within DESI. And I think the most interesting one is this bottom one, 22 EMF. You can see here the spectra by DESI was actually taken before there was any sort of detection by a wide field survey. So we have so this sort of opens the possibility for even coincidental infant observations, allowing us to basically get things within minutes then, just by getting lucky sort of by observing so many galaxies. The other interesting fact is that we were able to go with these sort of spare fiber programs down to about 22.5 magnitudes and sort of in GR and I. And we basically were able to do this because it's just such a high throughput. And then so in dark time, we reached these really, really deep limits. And I think this is about, I think, the limits you would want to go with Keck and LRIS. And we're getting this with DESI on a 4-meter telescope just because there's such high throughput with this instrument. And that basically lets us push out to these sort of intermediate redshifts for 1As, which is sort of very important to sort of narrowing down the cosmology and getting good measurements. Another sort of interesting fact is, so DESI's already gone through the sky, mostly finished this main survey program. And as we start observing the same areas again, we're going to get supernova in regions that have already been observed. And basically we have transients. So this, for example, is a type 2 supernova where it was very nuclear. And basically we already had a DESI spectra of that galaxy. And then we put a new fiber to get the supernova spectra. And it's sort of hard to see, the original, you can see maybe a little bit of a bump, but it's hard to sort of tell how much that is from a new transient. But when you can subtract, and the subtraction is very easy because it's the same instrument, the same calibration, same everything. So you can just do a one-to-one subtraction. You have the same, area of the fiber as well, and you can just get these really nice subtractions. It's also pretty interesting for massive black hole binaries. This is a massive black hole binary candidate. So we have one spectra from 5 years ago, another spectra from 2 years ago, and you can just compare them one to one, and you can sort of see that the broad H alpha regions are sort of evolving as a function of time. Another sort of effort that we've undergone with DESI is that basically the DESI goes 9 square degrees. Rubin is also about 9 square degrees. So we basically took DESI and we pointed it in the Cosmos field, and you can see all the little red and purple dots. The red dots are things that we're able to actually successfully place a fiber on. And there's about 70 transients in that plot. We were able to get spectra of about 40 of them just in one go. And basically that became 50% of the transients in the Rubin field. And we're like, these are very low quality cuts. So there's a lot of garbage that unfortunately gets in, but it's sort of proving the point that you can just get hundreds of transient spectra all at once, just using this sort of instrument. And so we did this twice, and we were able to target about 345 different transients from Rubin. About 63 were variable stars, 56 were AGN, and then we had 5 supernova. So I released this in an Astronaut, and I encourage you to go read it. It's a lot of fun. Just being able to target and go through so many spectra all at once. Finally, I want to sort of highlight DESI and its importance to sort of being able to help localize gravitational wave events. So there's a subsolar mass merger that we talked a bit about, 018K, and its possible counterpart, 2022 LZ. But basically, ZTF observed this within a few hours, and there's basically 58 candidates, and they highlighted one, which is ULZ. But a sort of really important part of this was that we were able to localize ULZ almost instantly with DESI, because we basically have DESI spectra of this entire region of sky. You can sort of narrow down localizations, and there were basically 152 transients that were reported to TNS, and of those, 73 already had pre-existing DESI redshifts. So we're able to sort of exclude 58 of these immediately, and then sort of narrow it down to 15. There's been a lot of talk using Trove to sort of narrow it down, but I think the best ability we have to narrow these down are going to be these giant spectroscopic catalogs, especially from DESI, as it this becomes publicly released, but then also from Foremost, other these just giant spectroscopic catalogs that will help us narrow down and localize these events as as we go into sort of IR1 in the future. So in conclusion, we've been using the DESI fiber to sort of get spectroscopic classifications of sort of thousands of transients down to 22.5. We use this sort of dedicated tile program in the LSST to drilling fields to get hundreds of transients sort of in one go. And then we're also just sort of using DESI as this very important catalog to sort of localize gravitational wave events instantly. And then I guess the sort of question I have for everyone is, we have all these spectra of variable stars and AGN, and how should we sort of share these? Because I assume we don't want to be polluting the TNS with a bunch of variable stars. So yeah, thank you.
Thanks. Thanks. Any questions for Sander? Dave.
So is there, maybe you could talk about the future, what the plans are in the LSST era for DESI follow-up.
Yeah.
Yeah.
So I mean, so for the dedicated tile program, we have sort of approval to observe every 2 weeks with the dedicated tile, one in bright time and one in dark time. And eventually there are sort of plans to, as we move into sort of the DESI 2 era, to make it an even larger part of sort of DESI 2 transient follow-up, especially the 1A cosmology section of it.
What is DESI 2? Is what Masi asked.
I think it's still unclear exactly what it's going to do, but it's supposed to be just another 5-year survey. And I think there's hopes to move it to the south is, I think, the main thing.
Given that DESI's data is private, is that a problem with publishing all of these in the TNS, or like is there
well, so the paper I released about the spare fiber program lets us publish up to 1,000 spectra sort of to TNS and such. And then we got special approval for the dedicated tile with the DDFs to publish the spectra. So,
okay. Any more questions, Gotham?
Yeah, on the subject of variable stars on SN spectra, or even spectra of SN that are fairly common, if they're at different phases from what we have on WISE-REP on TNS, they're still valuable. I would chuck the lot on Zenodo and advertise that it's there, just because one of the biggest challenges with making simulations in any band particularly for Rubin, but soon for Roman, is to have an underlying SED model of these things, and having time series SED models for everything would be actually quite helpful.
Yeah, I also wouldn't be mad about putting all of those in the TNS.
I feel like TNS is supposed to be for supernova, not variable stars, but Zenodo, yeah.
Ryan.
On the last point, have you thought of talking to the folks at Astro Data Lab to maybe put the spectra there? I know Stephanie Juneau has like a Sparkle tool to look at DESI spectra, so that could be a good opportunity to open it up to other.
Yeah, we have been talking to the DESI survey op team about like being able to have a special. So there's a DESI Galaxy viewer for DR1, just to be able to sort of have that as an option to view these spectra as well, sort of publicly. And then you would be some website where you could like put to take you to all of the various things, and also matching them to what their Rubin counterparts would be. Yeah, something we're looking into.
Lynn?
Is there any plan to target the Roman high galactic latitude time domain field?
Not yet. I mean, so there is a plan to sort of do a large scale dedicated 1A follow-up, which would be trying to target 1As from both Roman and Rubin to get a really nice spectroscopic sample of 1As for, to help improve DESI cosmology. That's about as far as we've thought about Roman.
Relatedly to Lynn's question, what's the limiting magnitude?
22.5 is sort of the limit for dark field. So Roman's going to go a lot deeper than we can, but there is some investigation for DESI 2 about doing like full like 2 to 3 hour exposures to go down to 24. So.
Any other questions? If not, we will move on to the discussion section. We can still have more questions. Let's thank Sander again.